Hi everybody, and welcome to my 11th beam video. This video I'm going to be solving this problem here. I'm going to be finding the maximum bending stress in this beam with this channel shaped cross section, and I'm going to find its position of the maximum bending stress, both x, so where it occurs, and y, so which point on the cross section here does it occur. So we know that the equation for bending stress is this. Alright, so we basically just need to go through and find all these variables, so I and M. Alright, so let's start with the bending moment. So it's going to require us to get a free body diagram of the whole thing to find the reactions, and then go in making a free body diagram of the two sections, like this, and then get the bending moment from that. So I'm going to go ahead and speed through that. Right, so the magnitude of this force is the 150 kilonewtons per meter times the number of meters, in this case 13. So 150 times 13. Okay, so now that we have the reactions, we can go in and take a look at each one of these free body diagrams we have here to find our bending moment. Alright, and then we still have this force from this distributed load acting on here. Just because we collapsed it into 1950 for the purpose of the overall free body diagram, that was just for that free body diagram. When we take a look at a section, we have to pretend this never existed and look at a section of this piece here, because in reality that force is applied over the whole thing. The magnitude of that force then is equal to 150 kilonewtons per meter times the number of meters, x number of meters. So we go ahead and summing up the forces and summing up the moments. I'll take the moments around this cut because that will make it so I use the 366, and I know that reaction because I found it here. If I would have took the moment around here, I would need to know V1, and I'd have to find V1 and then the moment. There's a chance I can make a mistake finding the shear force, and then that would also go over into my moment. So it's best to always take it about the cut edge. Alright, you're probably wondering why I bothered to find a shear force since we only need bending moment. But later on when we're finding the maximum value of bending moment, that will be when our shear force is 0. So if we already have the equation, we don't need to go through the whole process of taking the derivative of this. Okay, so moving into the second free body diagram of this chunk, I decided to look this way this time just because to show you it can be done. Probably a little easier to look the other way though. Alright, so two things here. I like to take my x starting from the position where my new free body diagram is going to start to count. So that's right after where this force is applied. That simply is because when now I develop my equation, it knows that, or I've told it to be, that x is going to start here. So when I go to graph my bending moment diagram, I can just take my Cartesian coordinate system to start right there and it'll make my life easier. If I would take x to be this whole distance, my equation would only apply for certain values of x. And then I'd also have to plot that graph starting out here somewhere. And I always think it's harder to plot a graph that's out here, trying to decipher it, than just knowing that it's based at x equals 0 and then right away knowing your y-intercept. Alright, but it's up to you. I like to do it this way, and then of course this length here is going to be 8 meters. Now the magnitude of this force is going to be 150 kilonewtons per meter times the number of meters. Well, the number of meters is 8 plus x. So I can say alright, and we can go ahead and sum up the forces. Not really important to notice, but we'll just do it anyway since we're at it. Later on when we do shear forces and beams and we compare it to bending moments, it's useful to know this. Again, taking the moments about the cut. Alright, this 8 plus x by 2, that's just the center of this distribution, which is where this force is going to act because it has a square distribution. And then we can say alright, I'm not going to bother to go through and simplify it because we can find the information that we need just based off of this equation right here. So now that we have the bending moment, let's just plot it to find the locations of things. Alright, so that's just a quick redrawing of the whole bending moment situation. So, bending moment for the first piece, when x is 0, it's 0. And then it's going out in a negative quadratic. So it's going to go out like that. Up until it reaches some value, and then down. I'll draw it in red, because I like red better. Alright, and right at the top here is the maximum value. And you can find the location of the maximum value by taking the derivative of this, setting it to 0, and solving for where that occurs on x. And if you remember, the derivative of m with respect to x is v. So if we just take a look at v1 and solve this where it equals 0, so 0, 366 divided by 150, we find that the position at which this occurs is and the magnitude of it at this point is alright, but we also have a value down here that's even bigger, and we can get that by solving for this equation at x equals 8. So this is negative, but in terms of magnitude it's bigger. So this is probably the one we're going to need to use in our final equation. And m2, if you solve at x equals 0, you get this number, and then it's going to rise quadratically to 0 as we go on like this. Alright, so there's a bending moment diagram. Alright, it looks pretty cool. So, the next step then is to find the moment of inertia. Alright, and that's the moment of inertia of this channel section about its own centroid. So we need to first find the location of the centroid, and then we need to calculate the moment of inertia about it. So overall, we know that for moment of inertia, we need to use the first moment of area Q. And for this cross section, Q of the overall thing must equal to the sum of the Q of the individual pieces. Alright, Q equals Q. So we can say, knowing that Q equals to y of the centroid times the area of that piece, we could say that Q overall is alright, and for our specific situation we have 3 pieces, so we can write alright, so now it's just a matter of finding these variables and solving them. So if you check out one of my other videos, one of my bonus videos, I talk explicitly about finding the centroid, and I explain how I do that. And I'm just going to quickly run through it here, and I'm going to use a table just to keep everything straight. Alright, so let's just put some dimensions back in here. We know the overall width. Alright, so now what sections do we take? We can allow the sections to run all the way up like this, or we can cut them off here. It doesn't really matter. As long as you stay consistent, I choose to cut them off here. So y bar, that's just the y bar, the centroid of each of these pieces. And the distance from this axis here, where y is 0. Alright, this is just simply this equation here, and I've added up all the y bars times their respective areas. Turns out the location of the centroid is 0.061 meters above the bottom. Makes sense. It's above the centroid of the individual pieces, and it's not in this region here. Alright, so the moment of inertia. We know that the moment of inertia of a single piece of something about its centroid is bh cubed by 12. And something that's rotating about another axis, we need to add a distance squared times the area of that piece. Alright, this is the parallel axes theorem. Now in this case, this is our centroidal axis, and all of these pieces are not located on that centroidal axis, so we need to use the parallel axes theorem. So once again, I'll just expand my piece of the table. Alright, so this is the moment of inertia about its centroid, the distance away squared times a, and then I add up the total moment of inertia for that individual piece. So using bh cubed and just plugging in for bh, and in this case bh, we get and the distances here are going to be the locations of these centroids of our pieces away from this axis. So it's just some simple minusing. Right, and the total moment of inertia is just this column plus this column. Then of course the total moment of inertia of the whole section, what we're after, is just the sum of these, and it turns out to be alright, and everything's been in meters, so we get meters to the 4. Alright, now finally we've got all the pieces we need. Let's go in to calculate the maximum bending stress. So that's going to be the maximum bending moment in terms of magnitude. And then we also need to take into consideration the distance away. Alright, so the distance away, in our case, is going to be the distance from the centroid to the bottom or to the top. So the distance from the bottom to the centroid is bigger, so that's going to be a negative y value. And it's just going to be this value here. Alright, I left the negative in. I could have taken it out and then just said the magnitudes, but it turns out, you solve this, that the maximum value is alright, so just a quick comment on this channel sort of section. You have to be careful because sometimes it won't just be asking you for the maximum stress, to ask you for some value like what does D need to be. And in that case you might need to check more than one point on a beam, because C1, or what is commonly called this here, these values could be different, and then if these values are different, then you might have to check both places to find the location or the magnitude of something else. Alright, so just be watch out for that. But for the rest, it's all about just following that process, using a handy table, making clear free body diagrams, and just plowing through it. All right, thanks so much. Hope it helped, and I'll see you around.